Good morning, everyone. I'm delighted to welcome you all today. Today, we'll be exploring the fascinating world of cleanroom airlocks. My name is Dr. S.K. Singh, and I hold a PhD in this field. On this first slide, I'd like to introduce the topic and set the stage for what's ahead. We'll be covering key aspects of cleanroom airlocks, their importance, and how they contribute to maintaining sterile environments. So, let's dive in and discover the critical role these airlocks play in various industries. Thank you for joining me, and I look forward to sharing this knowledge with you. Let's talk about the cleanroom airlock. An airlock is essentially a transitional space, positioned between areas with different levels of cleanliness. Its main purpose is to control the airflow and prevent contamination from entering or leaving these sensitive environments when personnel or materials move in and out. Why is this so important? Well, maintaining the integrity of the cleanroom and ensuring product sterility depend heavily on these airlocks functioning properly. They act as a barrier, keeping contaminants at bay and protecting the environment. Now, where do we typically find airlocks in practice? Common placements include between a corridor and a cleanroom, such as when moving from a grade C to a grade B environment, or between changing or gowning rooms and the actual production zones. They are also crucial for material transfer. Think of moving equipment or containers into a sterile area. For example, when material enters an ISO 5 aseptic suite, it must go through a material airlock. This ensures that the right pressure cascade is maintained and helps prevent any contamination from slipping in. So, in essence, airlocks are vital components that help us preserve the strict cleanliness standards required in these environments. These documents don't prescribe specific hardware requirements. Instead, they focus on ensuring contamination control through thoughtful design, qualification, and operational controls. When it comes to regulatory and GMP requirements, there are several key standards that govern airlocks. For example, the EU GMP Annex 1 emphasizes the importance of pressure cascades and controlled transitions between different clean grades. This helps prevent contamination from spreading. The FDA's 21 CFR Part 211.42 also highlights the need for environmental control, especially in sterile production areas. Similarly, the WHO GMP standards specify the use of pressure differentials and airlocks between different clean zones to maintain product integrity. And finally, the ISO 14644 series provides detailed guidance on cleanroom design and separation devices to ensure proper environmental control. All these standards are interconnected and emphasize that controlling airflow and pressure is essential for maintaining a sterile and contamination-free environment. Linking this back to our overall theme, it's clear that a well-designed contamination control system is fundamental for regulatory compliance and product safety. Now, let's talk about the primary functions of airlocks. First, they create a pressure barrier to maintain a clean environment. This means they help control the airflow, making it less likely for contaminants to enter. Second, they prevent contaminants from entering critical zones during entry and exit. This is crucial for maintaining the integrity of our clean areas. Third, airlocks facilitate the transition of materials and personnel without compromising the environment. They act as a controlled gateway, ensuring that nothing unwanted gets in. A logical point to remember is that without an airlock, when the doors open at the same time, air can flow freely between spaces. This free flow can carry contaminants into higher grade areas, which would break the strict cleanroom controls we need to maintain. So essentially, airlocks are vital for preserving the cleanliness and safety of our environment, especially during transitions. Let's talk about the cleanroom grade cascade and airlock system. Typically, we establish a pressure cascade, which means we have a hierarchy from grade A down to grade D. The idea is that pressure is maintained in such a way that the cleaner areas are kept at higher pressure than the less clean areas. For example, grade A is at the highest pressure, followed by grade B, then grade C, and finally grade D. Airlocks play a crucial role here because they act as buffers, helping us maintain these pressure gradients. The typical pressure difference set points are around 10 to 15 pascals between adjacent grades, and at least 12.5 pascals between classified and non-classified areas. This helps prevent contamination from moving between zones. Now let's look at the types of airlocks. First, we have cascade airlocks, which are used between two spaces with different pressures. Like between grade B and grade C then, there are bubble airlocks, where the pressure inside is higher than on both sides, creating a strong barrier, useful when we need a very tight seal. Finally, sink airlocks have lower pressure inside, often used in containment or biocontainment environments. The choice of airlock type depends on the level of contamination risk and whether hazardous materials are involved. So, selecting the right system is key to maintaining the integrity of the cleanroom environment and ensuring safety. Let's take a closer look at the design features and controls that are essential for these systems. First, we have the interlocking doors. These are crucial because they prevent both doors from opening at the same time, which helps maintain the integrity of the sterile environment. Next, there's pressure monitoring with alarms, which involves continuous differential tracking to ensure that pressure conditions stay within the required parameters. This is vital for safety and compliance. If needed, we also incorporate HEPA filtration, providing a dynamic airlock clean air supply. This helps keep the environment free of contaminants. And finally, we emphasize the importance of smooth, cleanable surfaces like stainless steel. These surfaces are easy to clean and disinfect, supporting overall hygiene. All of these controls are designed to ensure the integrity of the environment and help us stay compliant with GMP standards on a daily basis. They work together to create a reliable, safe, and sterile process. Let's talk about the air change rate and airlocks. A good rule of thumb here is that airlocks should have a higher air change rate, typically around 20 OC or more. This helps to quickly clear out any contaminants that might be introduced during traffic, like when people or materials pass through. For example, if we calculate the volume of an airlock that's 4 meters long, 3 meters wide, and 2.5 meters high, we get 30 cubic meters. To achieve 20 air changes per hour, we need an airflow of about 600 cubic meters per hour. If the airflow supplied is less than that, contaminants tend to linger longer inside the airlock, which can increase the risk of contamination spreading into cleaner zones. The main idea here is that more frequent dilution, or higher air change rates, helps minimize the number of particles and contaminants entering the clean areas. This is a key strategy to maintain a safe and controlled environment throughout the facility. Let's take a closer look at differential pressure calculation. The core idea here is that positive flow must always be maintained from the cleaner area to the less clean area. This helps prevent contamination from spreading. We start with some basic assumptions. For a clean room classified as grade B, we set a baseline pressure of 200 pascals. Adjacent to it, an area graded as C has a pressure of 190 pascals. To ensure proper airflow direction, we need a differential of at least 10 pascals. If we measure the pressure difference and find it to be only 8 pascals, that's not compliant. In that case, we would need to adjust the HVAC system or dampers to increase the pressure difference. This process is crucial because it guarantees unidirectional airflow across thresholds, maintaining the integrity of the cleanroom environment and minimizing contamination risks. Let's talk about interlocking and timing logic. Interlocks are absolutely essential in this system because they help prevent situations where both doors might be open at the same time, which could compromise the barrier. They also make sure that the sequence of door operations happens smoothly and safely, meaning one door closes and locks before the next one opens. For example, the logic might be, if the inner door is open, then the outer door must be locked. Conversely, if the outer door is open, the inner door needs to be locked. Additionally, the system might only allow door B to open when door A is fully closed and the pressure inside is stable. This kind of logic is crucial because it effectively guards against contamination pathways. By controlling door access in a strict sequence, we minimize the risk of cross-contamination between different areas. In the bigger picture, these interlocks and timing controls are fundamental to maintaining the integrity of the barrier system and ensuring safety and sterility throughout the process. Now, let's discuss the key aspects of the operational qualification, or OQ, for airlocks. First, it's essential to verify that the pressure differential control is functioning correctly at the designated set points. This means ensuring the airlock maintains the proper pressure levels to prevent contamination or air ingress. Next, we need to test the interlock functions and alarms. These safety features are critical. They ensure that the system responds appropriately if, for example, doors are opened unexpectedly or if pressure thresholds are breached. We also have to measure the air changes per hour, or ACH, in the airlock when it's under load. This helps confirm that the air exchange rate is sufficient to maintain environmental integrity during operation. Finally, the door operation sequences should be thoroughly tested. That involves verifying that doors open and close in the correct order, preventing any accidental breaches of pressure or contamination. To give you a practical example, the OQ protocol might specify checking that the airlock pressure stays at least 10 Pa above the adjacent lower-grade environment for 30 consecutive cycles. This kind of testing ensures consistent performance over time. All these points tie back to our overall goal, ensuring the airlock functions reliably and maintains the required environment, which is crucial for the integrity of the entire system. Performance qualification, or PQ, is all about testing the system under real-world conditions. It's not just about the ideal scenario, but about how it performs during actual usage. During PQ, we evaluate the system during peak shifts when activity is at its highest. This includes frequent door cycles, which are common in daily operations, and the overall traffic of materials and personnel moving in and out. The goal is to make sure that even during these busy times, the system maintains its integrity. Specifically, we need to demonstrate that it keeps a consistent level of pressure, manages air changes effectively, and that there are zero breaches. This thorough testing ensures the system can reliably support our critical processes, aligning with our overall goal of maintaining a controlled environment. Let's now talk about the documentation requirements. Key documents are essential to ensure everything is well planned and traceable throughout the process. First, we have the URS, or User Requirements Specification, along with the design specifications, which outline what the system needs to do and how it should be built. Next, there are the IQ, OQ, and PQ protocols and reports. These are critical validation documents that confirm the equipment and processes meet the specified requirements at different stages. We also need to keep daily pressure logs and alarms, which are vital for monitoring system performance and catching issues early. And finally, cleaning and maintenance SOPs, or standard operating procedures, ensure consistent and compliant practices for keeping equipment in good condition. All these documents form the backbone of a compliant and well-managed process, linking closely to our overall focus on quality, regulatory adherence, and operational excellence. Let's summarize the key points about airlocks in cleanrooms. First, airlocks are absolutely essential contamination control devices. They act as a buffer zone to prevent unwanted particles or microbes from entering the clean environment. It's crucial that these airlocks comply with GMP principles, pressure cascades, interlocks, and monitoring requirements to ensure they function correctly and safely. A well-designed and qualified airlock system isn't just about meeting standards. It directly impacts product safety and regulatory compliance. To achieve this, logical design is vital, and thorough qualification processes are necessary. This includes including calculations for airflow, pressure differentials, and timing in your qualification evidence. These details underpin the reliability and effectiveness of the system. Connecting all these points, a proper understanding and implementation of airlocks are central to maintaining the integrity of cleanrooms and ensuring that production processes meet strict quality standards. For further support, please don't hesitate to reach out to us. We're here to help with any questions or additional information you might need. Feel free to contact us through the provided channels. And with that, I want to thank you all sincerely for your time and attention today. Your engagement is truly appreciated, and I look forward to connecting with you again.